Hey everyone, and welcome. Thank you for watching. Today we will talk about feature pyramid network. Imagine you're looking at a picture. You can easily spot a tiny bird way up in the sky, and also a big car right in front of you. Your brain does this without even thinking. But for computers, it's a huge challenge. How do you teach a computer to see and identify objects that are super tiny, super big, and everything in between, all in the same picture? For a long time, this was a really tough problem for computer programs that try to see things, like those used in self-driving cars or security cameras. They struggled to be good at spotting all sizes of objects at once. Then came a clever idea called Feature Pyramid Network, or FPN. This smart new way of looking at images, introduced in 2017, completely changed how computers find objects of different sizes. It made them much better, faster, and more accurate. In this video, we'll break down what FPN is, why it's such a big deal, how it works, and how it helps computers understand our world better. In the past, to find objects of different sizes, computers often used something called an image pyramid. It's like taking your original photo and making many copies, each one a different size. Then, the computer would look for objects in each copy separately. This worked, but it was incredibly slow. Imagine having to scan the same picture multiple times. It also used up a lot of computer memory, making it impractical for real-time uses. As computers got smarter with deep learning, think of it as teaching a computer to learn from examples. People tried a faster way. They'd feed the image into a special kind of computer brain called a conv-net, short for convolutional network, and then try to find all objects from just one main output. This was quicker, but it wasn't very good at finding small objects. They often got missed because the main output wasn't detailed enough for tiny things. Now, conv-nets themselves inherently produce a multi-scale feature hierarchy. As an image passes through the network, each layer generates feature maps of different spatial resolutions. Early on, they see lots of detail, like lines and shapes, but don't really know what they're looking at. Deeper inside, they lose some detail but gain a better understanding of what objects are. The problem was, these early, detailed levels didn't have enough smartness to recognize objects well. And the deep, smart levels had lost too much detail to find tiny objects accurately. It was like having a super detailed map but no idea what the symbols meant, or a map that understood everything but was too blurry to see the small streets. FPN's big idea was simple. Why don't we combine the best parts of all these levels? Let's take the smartness from the deep layers and mix it with the detail from the early layers. The goal was to create a new set of smart maps where every level, from the most detailed to the least, understood what it was seeing, and to do it super fast from just one picture. FPN achieves this through three key pathways. The bottom-up pathway. This is just the normal way a conv-net processes an image. As the image goes through the network, it creates a series of feature maps, basically, different versions of the image that highlight certain features. Each step makes the map smaller but adds more understanding of what's in the picture. These are our starting points. Now, we start from the deepest, smartest map, like C5. We then upsample it, which means we make it bigger, like zooming in on a photo. This gives us a larger map that still has all that great understanding from the deep layers. We keep doing this, making the maps progressively bigger. This is the clever part. As we make the smart maps bigger, from the looking down path, we connect them with the detailed maps from the looking up path. Why? Because the looking up maps, even if they're not as smart, have very precise location information. They know exactly where things are. So, we take a detailed map, clean it up a bit, then add it to the smart map that we've made bigger. This mixes the smartness with the detail. Finally, we smooth out the new combined map. This process creates a new set of maps, P2, P3, P4, P5, where every level is both smart, semantically rich, and detailed, spatially precise. FPN wasn't just a small step forward, it was a giant leap. Here's why it made such a difference. Smart features at all sizes. FPN's biggest win is that every level of its smart maps has strong, high-level understanding. This is super important for finding tiny objects that used to get lost. Fast and efficient. FPN creates these powerful multi-size maps from just one original image. This means no more slow, memory-hogging image pyramids. FPN-based systems can work in real time, like 5 pictures per second, which is crucial for things like self-driving cars. Super accurate. FPN achieved amazing results in tough computer vision competitions, even beating complex systems without needing any extra tricks. It significantly improved how well computers could find objects, especially small ones. Consistent training. With FPN, the same system can be used for both teaching the computer and for actually using it. This makes the whole process smoother and more reliable. FPN isn't just a cool idea, it's a practical tool used in many computer vision systems to make them better. In object detection, there's usually a first step where the computer tries to guess where objects might be. This is done by something called an RPN. FPN helps RPN by giving it smart maps at every size. This means the RPN can now suggest objects of all sizes, from tiny to huge, much more accurately. After the RPN suggests possible object locations, other parts of the system, like fast RCNN, refine those guesses and identify the objects. FPN helps here too. It makes sure that each guessed object, no matter its size, gets processed using the most appropriate smart map level. So, a small object gets analyzed with a detailed, smart map, and a large object with a broader, smart map. This makes the final detection much more precise, especially for small objects. FPN's usefulness goes beyond just drawing boxes. It can also help computers draw exact outlines around objects, a task called segmentation. FPN makes this process faster and more accurate, especially for small objects, by providing those excellent multi-scale smart maps. The feature pyramid network is a brilliant example of how a simple, clever idea can make a huge difference in deep learning. It showed that even with powerful computer brains, it's still super important to specifically deal with objects of different sizes using these pyramid ideas. FPN got rid of the old, slow ways of handling different object sizes, making computer vision practical, accurate, and efficient for real-world uses. From helping self-driving cars see the road clearly to improving how computers analyze medical images, FPN is still a core part of how modern object detection systems work. Its ideas continue to inspire new breakthroughs in how machines understand our complex world, one object at a time. If you found this explanation of feature pyramid networks helpful, please hit the like button, subscribe to the channel, and let me know in the comments what other complex topics you'd like us to simplify. Thanks for watching.